so a few announcements. Hopefully all of you saw the announcements I posted on Piazza. Where, yeah. So if you have grading questions, some of you had a bunch of good grading questions, and often it's you tend to forget them as the end of the semester approaches. So please try to look back, and this week and the next are when you should come by. Okay, this week is better because next week I will be traveling, although the TAs will be here. So this week is a little bit better. So the other thing that I forgot maybe to mention is that, I mean, as you all know, of course, the final is next Wednesday, and sorry, Tuesday. It's Wednesday. Yeah. So. And in the same place, okay, so it will be very similar to the midterm. But more importantly, I think you should know that we'll most likely grade the final on Friday or Saturday. So, and they will be posted. If you'd like your answer sheets, if you'd like to look at them, then you should come by on Monday. Because Tuesday onwards I will be traveling, and after that the grades will be due before I come back. Okay? So if you want to look at your finals, graded final. Okay, so this is Monday, I think December 16th. Yeah. I mean, I'll probably be around until noon. Yeah.
How much emphasis do you intend to put on the pre-midterm?
Oh, in the final? Yeah, it'll be around 50% of the pre-midterm and 50% post-midterm. Yeah, mainly because I think post-midterm, I guess the topics we covered are a bit more advanced than the ones pre-midterm, so yeah, it'll be a mix of everything.
Can you turn on the front lights?
Oh, yes. I don't know if this is too bright. This is better? Okay. Okay, so this is so this is an important announcement that you should keep in mind. Yeah, I guess the university policy does not allow you to like take the final exam home, but you can definitely come by, look at it, and ask if you have questions. All right. So that's so those are a way of announcements, and as you all know, the makeup homework is due tomorrow.
Thursday.
Oh yeah, sorry, I meant next class. Yeah, sorry, I always think in terms of like next class is yeah. Okay, so due Thursday, usual, and up to Sunday. 10%. Okay. Right, good. So these are the basic announcements. Okay, so I wanted to start with a recap of what we've been doing at the very end, and then slowly we'll get back. Okay, so and today I also wanted to give you one example of a reduction because we've never seen any proper reduction. So yeah, I'll probably do continue this topic until about 11:30 or so. Okay, so this is what we've been looking at. So we were looking at complexity classes, and we said that we saw two basic classes. One is P, which is set of all decision problems that can be solved in polynomial time, and NP is set of all decision problems for which there is a polytime verification algorithm. Okay, and this is a very useful notion. This is a very important notion, and a verification algorithm consists of basically, we thought of it as like a prover and a verifier, and both of them have access to this instance I, instance of the problem, and a verifier is just it is a so this is some polytime algorithm. Okay. And so the prover is supposed to produce some W, which we call the witness or the certificate. And it sends to the verifier, and the verifier takes the instance and the certificate, and it outputs yes or no. So this is the general system we have. The framework. And a valid verification procedure is one that accepts only if this is a yes instance. So let's we saw the example of independent set. We saw the example of Boolean satisfiability and so on. So if the answer to the original instance is yes, then the prover should be able to convince the verifier that the answer is yes. Otherwise, there should be no way of convincing the verifier to accept. Okay. So this is NP, and we also saw this notion of reductions between problems, right? So we said that a polynomial time reduction from problem A to problem B is some transformation between instances. Okay, so we had this figure where you have instances of A, instance of B, okay, and these are both decision problems. So every instance of A is either a yes instance or a no instance, and these are of course all infinite sized sets, right? So these are all possible instances of all possible sizes, and the key thing is that this transformation T should run in polynomial time. And yeah, and of course T has no idea if it's a yes instance or no instance, and it must have the property that yes instances of A map to yes instances of B, and yes instances of no instances map to no instances. And these are the things you've got to prove about reduction. Okay, and we'll see I guess a formal example of a reduction today. And we said that we defined the notions of NP hard and NP complete. Okay, and these are of course very important notions. Problem A is we say that it's NP hard. Again, both of these apply to decision problems only. So A is NP hard if Boolean satisfiability, this is a problem that we saw last time, I'll recap it in a bit, if this problem reduces to A. Okay, so that's what we said. So by the way, also we said we introduced this notation of A reduces to B with under some polytime reduction. That's what we denote by this. Okay, and yeah, and as I was saying, you write it this way because it's like saying A is a little bit easier than B. Okay. Like if B can be solved in polynomial time, then so can A. So that's why we write it like this. Okay. So a problem is NP hard if it is in some sense harder than Boolean sat. Okay. So that's the intuition. So if Boolean set reduces to this problem. And a problem is NP complete if you have reductions in both directions. So if problem A, yeah, so if there's a reduction from A to Boolean set and vice versa. So yeah, so let me write down some obvious conclusions of this, implications of this. So corollary. Okay, so that's one. And another one is NP complete if it is in NP if both of these okay, so these are two corollaries. Okay, so this one's obvious, and this one is saying that you can replace this condition of A reduces to Boolean sat. Let me just write sat because Boolean sat is usually denoted by sat. So A reduces to sat is equivalent to saying A is an NP. So this was what we called the Cook-Levin theorem last time. So that's why this is an equivalent definition of NP completeness. Yeah.
So just to clarify, problem, let's say a problem in P it meets condition A but not condition B.
No. Yes. So right. Yes, any problem in P is also in NP, right? So this is what we saw last time. So yeah, it meets condition A, but it does not meet. Right. So any more questions about this? Because these are like very important notions that you should understand. And yeah.
You mentioned it last time, but can you repeat what you mean by like can replace with independent set like for a
Oh yeah. So he's asking about this thing in parentheses. Why can you replace Boolean sat with independent set? So it turns out, as we'll see later in today's lecture, that so it turns out that Boolean sat reduces to independent set. Okay, so this is what we will see in today's lecture. Okay, so the nice thing about reductions is that they are associative, not associative. They're transitive, right? So in the sense that if Boolean set reduces to this and independent set reduces to something else, to problem A, then there's also a reduction from Boolean sat to problem. Okay. So this means that to show NP hardness, you can actually show that this reduces to this, okay, because there's a well-known reduction from this problem to this. Right? So yeah, so that's why I have that. Is there any other question? Alright. So what is Boolean SAT? So Boolean SAT was this problem where you have a Boolean circuit. So it is basically something that has, it computes some, it has some output gate which I will call F, okay, and it has a bunch of inputs. So these are called x1, x2 to xn. These are inputs to the circuit, okay, and then and you have some AND and OR NOT gates. So this one AND, some OR something. Okay, so you have a whole bunch of gates. Each one gets a bunch of inputs, and you have multiple layers of this. And in the end, you output some function f. So I will denote this by f of x1, xn. Okay. So such a circuit is called, so this is what we call a Boolean circuit. Okay. So every gate is an AND or a NOT gate. And so the question is, given a circuit like this, okay, so given some circuit like this, is there a procedure that can tell if, is there a way to tell if there exists some inputs, x1 through xn, such that the output of this is true? Okay. So note that some circuits need not have this property, right? Like if you have a circuit that basically computes I don't know, x1 and x1 bar. Right? So such a circuit, I mean, there is no x1 that makes it output true. So that's the question. Like, is there are there assignments to x1 through xn such that the output, which is f, is equal to true? Okay. So this is called the circuit satisfiability problem. So, any questions on the problem statement? Okay, so this is a circuit satisfiability. I'll also call it Boolean SAT or simply SAT. Okay. Good. So this is one of the most basic problems in complexity, and as you can see, this is a decision problem. And the trivial algorithm for this is basically checking all possible assignments. So, in fact, people believe that for the general problem of satisfiability, doing something like 2 to the even n by 2 is difficult. Okay? Like the trivial algorithm takes time 2 to the n, roughly speaking, and we don't know if, for example, you can do 2 to the n by 2, and we believe that you cannot do it in general. Okay. So, conjecture that 2 to the little of n is impossible. So this is a little bit weaker, but this is still okay. So conjecture that 2 to the little of n is not possible. Okay. All right. So that's satisfiability. And one thing that's easy to see is that satisfiability is an NP. Which means that there is a verification procedure. And why is that? The reason, as we saw last time, is that so what you need to produce is some kind of a verification algorithm and a witness. Right? So the verification algorithm basically expects an assignment for which f becomes true, and it just verifies that that assignment satisfies. I mean that it just evaluates the circuit using those values of x provided, And if it's true, it outputs true, otherwise it outputs false. And clearly this solves the satisfiability problem, in the sense that if you have a valid input, then it will output yes, otherwise it will output yes. Okay. So yeah, we saw this last time, so I'm just glossing over it, but if you have any questions, feel free to ask. Right. So Boolean SAT is in some sense the canonical problem in NP. Okay, and this Cook-Levin theorem, which we again saw last time, says that any problem in NP has a polytime reduction to Boolean SAT. Okay. And this, as I was saying last time, is a somewhat non-trivial theorem, but the proof is it actually follows from the fact that there is some verification procedure. Okay. So the Cook-Levin theorem says that any problem in NP has a polytime reduction to SAT. So in some sense, SAT is like the hardest problem in NP. Okay. Alright, so this is roughly where we stopped last time. So we introduced this problem called 3-SAT, okay. So which is a special case of SAT. What is 3-SAT? So it's something like this, but this Boolean formula f has a very special structure. Okay. So here f looks like it's an AND of a bunch of what are called clauses. Okay, so and each clause is of the form it looks like this. Let me write down an example. It has some x1 or x2 bar or x3, something like this. Okay, so, but the point is that it has exactly 3 variables, okay, and it's either a variable or its negation. Okay, so such a thing is called a literal. Okay, so and each clause formally looks like some li1 or li2 or li3, where each li is either a variable or its negation. And I am allowing it right at this point to, or rather I am not allowing it to have the same thing repeat. Okay, so x1 is not equal, so I1 is not equal to I2. This is variable or okay, so this is 3-SAT, and this sort of a thing is called a conjunctive normal form, if you guys have know about it. And yeah, and I guess people came up with it first when they were thinking about grammars and so on. So that's when CNFs came in. But yeah, but you don't have to know anything about that. So you just have to think of it as a special kind of Boolean form. Okay. So because it's a special case, right? So it is here that 3 sat is easier than sat. Okay, so in some sense 3 sat. So then 3 sat reduces to sat just because it's a special case. But like I was saying last time, the general satisfiability problem also reduces to 3 sat. Which means, so yeah, actually, can you guys see how you, I mean, what is needed to be proved if you want to reduce something, if you want to actually show something like this? Yeah.
Maybe if we can show that we can make like and/or and not gates, and then show like we can also do some sort of induction where we can do like layers of them as well.
Right. So what he's saying is, you know, to both the problems look similar, except that here the formulas have some certain structure, right? So, but before that, any reduction is basically a transformation of instances, right? So you've got to take some instance I of sat and produce an instance I prime of 3 sat. And this is like this transformation procedure T that we talked about. So this must be some algorithm that takes an instance I of sat, produces an instance I prime of 3 sat, with the property that if this is a yes instance, that should be a yes instance for 3 sat, and if there's a no instance, it should be a no instance for 3 sat. Okay, so this is what one needs to do. So this is the meaning of this, right? So saying that there's a reduction like this is equivalent to saying this. So I'm just writing it down so that it's clear to those of you who haven't seen reductions before. Now, how do you do this? So this turns out to be, in this case, not so difficult. So the idea is like what you're saying. Right, so it is you want to convert an arbitrary formula I. So I is just some arbitrary circuit. You would like to convert that into something which looks like 3 sat, which has this special clause and OR structure. The way you do that is by saying that, okay, let me transform each gate. So an arbitrary formula has a bunch of gates. So let's say, yeah, again, let's assume that all these gates are binary. So they have 2 inputs, and then maybe these feed into, so this is an, let's say, an AND gate. This is, let's say, an OR gate, stuff like this. So the main idea turns out to be to effectively write out variables for the output of each gate. So to introduce new variables for the output of each gate. So this again, you don't have to fully understand this. I'm just saying it just to describe the main idea. So the idea is create new variables for the output of each gate. And imagine this is a binary circuit. Then, and yeah, so and let's say these are base variables. And let me show it for some simple circuit like this, and hopefully you will be convinced that you can do this sort of a transformation in general. Okay? So if you had a circuit like this, now the idea is to introduce new variables. So let's call this y1 to y2, and let's call this is basically f. Imagine that you are able to write y2 is identically equal to x1 and x2. So this holds, and y1 is identically equal to x3 or x4, and f is identically equal to y2 or y1. Imagine you could write something like this. Suppose this kind of expression is allowed. Okay, so where you have something of this kind, and finally you want f should be true. So I claim that this formula, this is a loosely defined Boolean formula, right? So this is like, oh, this is a procedure that is checking if y2 is equal to x1 and x2, and y1 is equal to x3 or x4, and something like this. So this formula is logically equivalent to, so this formula is satisfiable if and only if f has a satisfying set. Do you guys agree with this? Can you repeat the last thing? So this formula, so this is, so far it's not a proper logical formula yet, but you can think of it as an algorithmic procedure, right? So this algorithmic procedure takes variables x1, x2, x3, x4, y1, y2, y3, y1, y2 and f. Okay, and it checks this. It checks all of these conditions, and it accepts if all of these conditions hold. Now I claim that this formula is satisfiable. That means there are assignments for all of these that make it true, if and only if this original formula is satisfied. So, yeah, intuitively the reason for this is that if all of these must be satisfiable, then firstly you must have y2 being equal to x1 and x2, otherwise it will not be satisfiable. So whatever these values are, so whatever you pick for x1, x2, x3, x4, y2 must be equal to x1 and x2, otherwise this part will not be satisfying. So in some sense you are forcing every value, every gate of this circuit to do the right thing. And right, so think about this for a while offline, because it's actually a nice thing if you understand. Okay, so, and the reason I did it this way is that now each of these clauses, so to speak, only consists of three things. Okay. So this is starting to look more and more like three-sided, right? So now you have these. Now you have whatever you want to compute expressed as an AND of a bunch of clauses, and each clause only involves three guys. So it's not quite an OR of three things, but now you can then introduce some more variables and force this to be like an OR of three. And that's the idea behind this proof. But first, any questions on this procedure? Because I see many of you don't. I think seeing this as a formula is something maybe you guys find tricky. Yeah, why don't I wait till someone asks this?
Yes, so that in statement is an example of whole statement on the bottom.
Yeah, so this is the
The problem.
yeah, this is the instance I of SAT. And I'm saying that this instance of I of SAT, I'm transforming it into this other instance. This is not quite an instance of 3SAT yet, but it looks like 3SAT in the sense that it's an AND of a bunch of clauses, and each clause involves exactly 3 variables. Okay. So, and some of them are variables that are newly introduced. Yeah.
Maybe you can translate CNF and make it very
Yeah. So from here, going to 3SAT is somewhat straightforward. Okay, like if you've seen these Boolean manipulations, this is straightforward. But this step is conceptually the more interesting one because you introduce new variables and stuff. Yeah.
Maybe I'm missing the point. The first statement doesn't have to be true, right? X1 and X2 don't have to be 1 for X to be 1 for X to be true.
Correct. Yeah. But what this is saying, this clause would be satisfied if and only if y2 is equal to this. So in this case, like y2 would all you have to do is y2 should be equal to this. Okay, so like this could be true, this could be false, and then this whole thing would be true if this guy was false. All this is enforcing is that this gate is doing the right thing. Okay? Yeah. So you can interpret this this thing as this formula is basically saying, oh, this gate is doing the right thing, this gate is doing the right thing, this gate is doing the right thing, and the final thing is true. Okay? And anything where that happens actually means that if you are able to produce excis for which that thing happens, for which that condition happens, it's like saying that this formula was satisfied. That's the general idea. Yeah.
So I guess my last question is, why does it matter that it's exactly 3 liminals for this problem?
Oh yeah, it doesn't matter. Anything more than 3 is also fine. Okay. Yeah. So anything more than 3 is fine. The reason I'm doing 3 is because going from 3SAT to my next problem, which is independent set, turns out to be nice. So yeah, so you should think of this whole game of reductions as you like to come up with problems that have a lot of structure, and you would like to show that those are also NP-hard. Okay, and then it makes it easier for you to prove that other problems are NP-hard. Okay. So yeah, so that's that's a good question. So good. So it turns out that 3SAT is also NP-hard, and so what that has shown is that what that reduction, that informal reduction has shown, is that you can transform an instance of SAT to an instance of 3SAT. Okay, such that this is satisfiable if and only if this guy is so. And now what you can show is that so what you can show is that 3SAT reduces to independent set. And this is where the nice structure of, you might say, why didn't I reduce the original satisfiability problem to independent set? Right? So that turns out to be messy because the original satisfiability problem has all kinds of gates and so on. So this kind of a specially structured SAT instance turns out to be much more easy to reduce to independent sets. Yeah.
Did you finish that proof?
Oh, that was a hand wavy proof? Yeah, so I
Are those like C1 and C2 and like?
Yeah, exactly. So these are supposed to correspond to C1. Actually, this will be converted into a bunch of clauses, which will ensure that, so those will,
Don't you just need to show like the base case or something?
yeah, so you have to say how you would convert something of this kind into a bunch of ORs, right? And this you can imagine is possible by just listing out. So there's a generic way, if you guys have any experience with like Boolean circuits, like if you have the truth table of something like this, okay, so you can
You just take two margins and then do another knock.
yeah, exactly. So there's this canonical way of converting any truth table into a CNF kind of a form. So let's not get into that because it's not very important. Okay. But the point is to note that here it's a bunch of ANDs, and each AND involves exactly 3 ways. Okay. So it's starting to look like 3 AND. Okay, so any other comments?
I just want to clarify, you mentioned in the preset that for each C, for instance, we should have 3 literals. I think you mentioned that, and here we have only 2. So
No, you have 3, right? So y2 is a variable. Y2 is a variable, x1 is a variable, and x2 is a variable.
but like in the preset, like they are joined together with OR gate, and here you are writing Y2.
Yeah, so this is what I was saying, like there is a way of now converting this into proper 3 SAT, which I am not going to say because it's a bit messy.
Okay.
Yeah.
You mean like it's equivalent?
Right. Yeah. So yeah, that's a good question. Yeah. And again, this is all, I'm just doing this to give you a sense of how this reduction works. Okay? So you don't have to really know. All right. So that's So this shows that even this satisfiability with this special structure is NP hard because SAT reduces to that. Yeah.
And 3 SAT reduced to SAT.
Oh yes. I claim yes. Can you see why?
Makes sense to me. So would that make it NP complete?
Yes.
Okay.
Yes. Yeah. So 3 SAT reduces to SAT for a trivial reason that it's a special case of SAT. Right. So the same formula can. So 3 SAT is an NP complete form. Okay. And so I was hoping to actually show this as an example of a reduction, but I don't think we have time. So I'll skip this, but I'll have a link to this. This is a very easy. This is somewhat easy proof, but it's going to take like 10 to 15 minutes, right? So so maybe I will just include a link to this. This is a fairly easy thing. And right, so you can. It turns out you can show that 3 SAT can be reduced to independent set, and here the reduction actually uses the structure of 3 SAT. Okay, that this is actually an OR of a bunch of things. So yeah. Okay, so take some instance I of 3 SAT, and you can now produce a graph G and some value of K. And what you can show is that I is yes for 3 SAT if and only if G has an independent set of size Q. And this is a nice thing to show, right? Because then it's basically showing the independent set problem, the decision version of it, where you're given a graph and you're asked to find if there exists an independent set of size k, showing that that problem is NP. Rather, this reduction shows that it's NP hard, but we also know that independent set is an NP, therefore it's NP. Yeah.
We know like k in terms of the 3-set problem, or is that?
Yeah. So this reduction is actually, I can very briefly outline it. So I can again outline it in the case of a special formula. Okay, so and you can try to figure out how it will work in the general case. So suppose I have a formula that we're going to take one example, x1 or x2 or x3 and x1 or x2 bar or 3 bar and let's say x1 bar. Okay, so this is an arbitrary, somewhat arbitrary formula that I'm picking, right? So let's say I have this formula. Now the goal is to come up with an instance of independent set, which is basically a graph and so forth, such that this formula is satisfiable if and only if that graph has an independent set of a certain size. Okay. So as you can imagine, this is a rather tricky thing, right? Because how do you convert a formula like this into some graph, right? So this is some formula phi, and you'd like to convert, and you'd now like to come up with a graph so that it has an independent set of a certain size if and only if this guy is satisfied. Okay. So any thoughts on how you might do this? Actually, if you can come up with this, it would be very remarkable. So let me just, I mean, it's unless you see it, it's impossible to come up with it. Okay? So, or if you think about it for long enough. So, clearly, like Cart came up with it from scratch. Okay, so the nice thing is, so the idea is for every such clause. So each clause, as I said, involves 3 variables. Now intuitively, each variable can take true or false values, right? So for each clause, imagine having actually another simpler question. So if I just had this clause, so just had something like x1, x2, x3, how many different assignments are there that actually make it satisfiable? Just that clause. So total, I mean, so each variable can be true or false. Okay. So there are 2 times 2 times 2, which is 8 assignments total that are possible. Of those 8, the only way this can be false is if all of them are false. Correct? Because there is an OR of a bunch of things. Okay. So for each clause, there are, so the observation is that, let me write it here. There are 7 I will call them like local assignments. It just means for the variables involved in those clauses. So 7 assignments. Oh yeah. 7. In this case, these are the only variables. So 7 assignments of variables that make the clause true. Okay. For every clause, you have 7 assignments that make this clause true. So let's write them down. Right? So here, these are like something like TFF, TFF, TFF. Okay. And imagine that these are okay, so these are I will call them like 7 vertices. Okay, and for each vertex there is some thing that is some assignment. Okay, so this one stands for TFF, this stands for TFT. So you have vertices for everyone except FFF. Okay, so there are 7 such things, and I will put a circle around them. Similarly, for this clause, you will have 7 such things. For this clause, I will have 7 such things. Okay. So this one corresponds to x1 being true, x2 being false, x3 being false. This one is the same thing. Okay. Now, and here you have some things. So now, these are the vertices of my graph. Okay, so there are 21 vertices, and there are 7 times 3. 3 clauses and 7 per clause. So these are the number of vertices. And I'm going to put a clique within each thing, within each such block. The idea of putting a clique is that I cannot select, in any independent set, I cannot select more than one from this group. Okay. So I will put a clique for between these guys, and so on. Okay. Similarly over here, so there is some clique. Okay. And right. So why am I doing this, right? So I would like to ensure that finding an independent set here somehow allows me to find an satisfying assignment with this form. Okay, so I'd like to ensure that independent set of size, in fact, independent set of size 3 over here allows me to find a satisfying assignment over here. Okay, 3 is the number of clauses. And yeah, so again, since we don't have too much time, so what I'll tell you the idea. So the idea is to first you have a clique here, and then you also have edges between vertices where the assignments don't match. Okay? Like here in this TFT, suppose you have a vertex here that says FFT. So there is an edge between these guys. If there's another TFT here, then there is no edge. But you have an edge between everything that does not match. Okay. And this forces consistency across variables. Okay. So this basically, so if you pick this and if you pick this guy, then it's not allowed, because somehow this is forcing you to assign f for the first variable, while this is forcing you to assign t for the first variable. So that's the sort of thing that can be done, and you can actually argue that there is an independent set of size 3 here, if and only if you can satisfy all 3 of these constraints. So that's the general idea, and the answer to his question is basically that, yeah, so the k will actually be equal to m, which is the number of clauses you have. And yeah, Yeah, and yeah, like you can see, reductions are a little bit clever. You just have to argue that having an independent set of certain size lets you recover an assignment. And you also have to show the other way around, which is that if there is a valid assignment, then there is actually a valid independent set of size. Okay. So let's not get too much into the details of this, but that's the idea. That somehow you can create a graph, okay, where having an independent set of size k is equivalent to this I that you start off with being a essence. Okay. So yeah, but if you haven't seen reductions before, some of these are very nice. So I will include a link to Jeff Erickson's notes because he has like a whole bunch of reductions. So you can reduce from like 3 set to independent set, from independent set to a whole bunch of other problems and so on. Okay, and yeah, so proving NP completeness used to be a field in itself for a long time. Okay. Alright, so let's, so this is what I was saying. So 3 set reduces to independent set, and because of transitivity, we saw that SAT reduces to 3 set, therefore SAT also reduces to independent set, which means that independent set is empty. Do something very simple. So the last thing that I just wanted to mention, which is which I guess is something we've seen in the course. Right? So for a bunch of problems, especially like set cover, vertex cover, and problems like this, we saw algorithms that are guaranteed to have some approximation solution. Right? So we said that if the optimum was k, then the solution you produce has size only like k log n. Right? That's what we said for set cover with this greedy algorithm. Right? And similarly for vertex cover, we said that if there is a solution using k vertices, then you produce 2 times k. This was one of the homework questions from a while ago. Okay, and one can ask if there are better algorithms for this, right? So you can ask, oh, okay, is there a better than factor 2 approximation for vertex cover, okay, or better than log n approximation for set cover? So one of the natural questions is, oh, okay, can you actually show that problems, I mean, in some sense that doing this is also impossible, assuming that, let's say, 3 SAT does not have polynomial time algorithm. Okay. So the general question we'd like to ask is something like this. Okay, so like, can problems be NP hard to solve approximately? So note that this is a different question than what we've been seeing, right? So here, these are implicitly optimization problems, right? So we are looking at problems like set cover and so on, and so the question, for example, is there for set cover with approximation ratio better. So better than log n, but I'll just say approximation ratio, let's say 5. Which is like asking, oh, if the optimum is k, will it always output like at most 5k? And one natural question is there a way to reason about things like this by using this technology of NP completeness reduction? Right? So it turns out that so you can actually rule out things like this. So you can say that no unless, so this is again like this picture, this cartoon picture that we keep seeing, right? It is that it's not just that I can't produce a good algorithm, nobody can. So no unless 3SAT has polygon. So it turns out you can make statements like this. Okay, so like if you, like for this question, like does set cover have factor 5 approximation algorithm? You can answer that no unless 3SAT has polygon. If you think about this, is a nice statement to make, right? Because you are ruling out very good approximation algorithms. So you are not just saying set cover cannot be solved in polynomial time exactly, but in fact there is no even an approximation algorithm for this. And this sort of a thing is called hardness of approximation. And yeah, so it turns out you can use a very similar framework to the one that we can use. Okay, so yeah, so let me skip that in the interest of time. So yeah, and but this is so one of the first non-trivial results of this kind is what is called the Pcp theorem, and what it shows is that in fact for the 3SAT problem, not only is it like NP hard to solve it exactly, but you also cannot approximate the number of satisfiable clauses. Okay, so suppose your goal is not just to find a satisfying assignment that satisfies all the clauses, but let's say you want to answer if 90% of the clauses are satisfied. So even that problem turns out to be NP. Okay, and that is shown first by what is called the Pcp theorem. Okay, and this is one of like the starting points to show hardness of approximation for various other problems. Alright, so yeah, so let's stop here, and I didn't find any questions on Piazza about course review. So are there specific topics that you would like me to just revisit next time?
Optimization.
Sorry?
The optimization.
Okay.
Because it didn't have, I'm not sure about that, but we do have any examples of,
Yeah, so homework 6 is has a couple of questions. Yeah. Yeah. Yeah, I can revisit briefly. Okay. I mean, it's a big topic, so let me. Maybe I will do a couple of examples. Is that good? Okay. Yeah, so I can do maybe a couple of, maybe an example from last year's final, something like that. That would illustrate. Yeah. Yeah.
Is there a practice final
So I had posted last year's finals and their solutions. So those are I think good things to look at. Yeah.